In this video, we are going to go over memory mapping, but for recursive code. So we talked a little bit in the last video about how to map memory and how to think about where stuff is stored on the heap or the stack. When you declare things, regular integers versus things that are allocated using the new keyword. And some of that allowed you to see how the stack frame builds up and destructs as you go in and out of functions. So I thought it would be good to go over what happens with a recursive function because, or a recursive call inside of a function, because a lot of the data structures that we're going to be dealing with are very recursive by nature. So we're going to be writing lots of recursive code, and understanding the memory of that code is also going to be really important. And so having this kind of visualization in your head will really help you as you kind of work on that code. We're going to use the most basic recursive algorithm, the factorial, because it's just really easy to think about. So the definition is just right here. So n factorial just means that you continue to multiply n times n minus 1 factorial until you get down to the base case when you have reached 1, basically. And the code looks something like this. You can see the recursive call is right here, and the base case is right here. So this is the case we're going to look at as we work through this memory mapping. So before we move forward, let's make sure that we understand the code. So what is the third thing printed when we call factorial 10? So that means that we're going to pass 10 into the factorial function. And right away, we can see that the first thing that happens in the function is it's printed. So 10 is going to get printed. Then we are going to go into an if statement. It's going to check if n equals 1. If it doesn't, which it doesn't, then it's going to go into the else, and then in the else is where the recursive statement happens. So here it's going to pass 9 in to factorial, which is just recursively changing, or recursively calling the function again, and so now you have 9 coming in. When 9 comes in, it's going to print. Same thing happens again. It's not 1, so it's going to recursively call again, but now it's 9, so it's going to pass in n minus 1, which would be 8 now. It goes up and calls the function again, then it becomes 8, and so 8 gets printed. So the third thing printed in this recursive call is going to be 8. So think about this as we're going through this code and thinking about how the memory is mapped. So we're going to use another memory diagram. Sometimes I have the memory diagram flipped and I have the heap on the top and the stack on the bottom, and then sometimes it's this way. I actually personally like this way better, but Professor Hummel liked it the other way, so last semester we used it the other way. So if I'm reusing examples from last semester, they're always going to be flipped. I didn't want to go through and actually change them. It's just a lot of finicking with PowerPoint is the real reason, but it's also nice for you to see both ways because it is just a visualization of what the memory looks like. I like to think of the stack growing down, probably because that's how it was taught to me. So it's like how it makes sense to me, and so that's what it is here. So we're going to look at how the memory in the factorial example looks like here in this kind of stack heap diagram. The other thing I wanted to point out, probably should have mentioned this in a different video, but there is a lot more to distinguishing the memory between the stack and the heap, and it's not even called the heap in some cases. So there is a bunch of technical, what would that word be? Jargon, maybe, about what precisely the space in memory is called when you call new, when you call malloc, etc., versus on the stack. But when I say the heap, I'm just talking about the place in memory that you can allocate and that you have permission to use. And that's typically what the word heap means. but if you like look into the technicalities of it, people use other words for it. So like free store is something you'll hear for C++. That's what it's called when you allocate using the new keyword. And none of that is really important. What's important is that you conceptually understand that there's this stack that like pops and pushes. Yeah, pushes and pops. And then there's the heap that doesn't do that. And that's all we really care about. We don't really care about the terminology too much, in case any of you are wondering. So in this case, we're only dealing with the stack and a bunch of function calls. So we have our main function here, which is going to call our recursive function. So this could be a helper function, or it could be it could just be the main function, or just wherever it's called. And so that's here right under main, and then inside of that factorial is called, so that stack grows down that first time. So the first one's easy to understand because you're passing 10 in and it's going into the the function. And so as you know with the stack, main calls my function calls factorial, and then factorial goes underneath. It's also showing like some of the local variables in those functions, or all of the local variables in the function. Okay, so that's what it basically looks like for the first call. So what does it look like as you continue through the recursion? So we went through 8 by hand, right, just now. We went through 10, 9, and 8. So which one of these is right for the next function call? So we did 10. So what happens when 9 is called? So this version here, it like puts the 9 variable inside of the same stack frame as the original 10. This one replaces the stack that was created from the first function call and just replaces it with 9. And then this, which is the right answer, creates another function call and puts it onto the stack. And that's what it is, because you are calling another function. And so every time you call a function, it pushes it onto the stack. And so as you can imagine, this memory that we're talking about that's called a stack is a stack. It's like a perfect abstraction for it. Every time the function call happens, you push something onto it, and then as we showed in the previous ones, as you return out of that function, it pops it off and it's gone, and it totally destructs everything that was there that wasn't allocated on the heap. So if we want to look at this with a longer recursive statement, let's look at it for x equals 4, because 10 is just too much to draw on the screen. So let's look at what the stack looks like as you call factorial 4. So first, you're going to have the first function call with n equals 4. Then you're going to have n equals 3, n equals 2, n equals 1. Now remember, that's the base case here. So for that if statement, you actually get returned out because it's the base case. And you start going back up. So you return and you send the result from, you send the result from the factorial 1 call into the factorial 2 call, which turns out to be 1. Then you return 2 into the one above it, return 6, return 24, and then ultimately you get your final answer of 24, which is 4 times 3 times 2 times 1. So that's kind of what that looks like. So if we can just do it one more time, when the my function calls factorial the first time, you get this stack. It builds onto the stack again for the second recursive call, then the third, and then the fourth, and then it's finished because it's reached the base case. It's going to return back. It sends that return back through the return statement, right? And so then the return statement becomes this function call, but in the one above it, right? And then it continues to return until it gets back. So that stack is getting built and destructed through that call. So there is some overhead with writing recursive functions for that reason, because that stack is getting created. And it is possible that it could lead to less efficient codes than iterative codes. But a lot of times what recursive calls are doing is not creating a bunch of new memory on each recursive call, because they're dealing with something that's maybe passed by reference, and it's actually allocated on the heap, and it's just altering that, or lots of other options. And so it can be written really efficiently as well. As you know, the recursive algorithms are really popular. So that's all I wanted to go over with memory mapping with recursion. We're going to be doing a lot more recursion as we move into trees. That's kind of the first data structure that is going to force us to really be thinking recursively. The algorithms are basically not possible to write cleanly in an iterative fashion. So this will kind of help as we start needing to map memory in recursive functions. So that's it. Thanks.